All right, so in this section, we're going to look at direct current circuits. Okay, so let me define what direct current circuits means. DC circuits are circuits where the current or voltage is constant in time. Okay, so what we call DC circuit, this is a circuit where current or voltage is constant in time. Current or voltage in the circuit is constant in time. Constant in time. This is the kind of voltage you get from a battery, okay? If you plot the voltage for a battery as a function of time, it will just be a constant, okay? For example, if it's a 6-volt battery, you always get 6 volts from it. And so the voltage and the current are going to be constant in time, all right? Now, so far we've defined a couple of devices. A capacitor, if you remember, is a device that stores charges or energy. We've also defined a resistor, which converts electrical energy to non-electrical energy. Today, we're going to define another device which converts non-electrical energy to electrical energy, such as a battery. Okay, we call it source. So a source is a device that converts non-electrical energy to electrical energy. This is a device that converts non-electrical energy to electrical energy. An example would be a battery. Example, you have a battery. What does a battery do? A battery converts chemical to electrical energy. This device converts chemical to electrical energy, How about a generator? A generator, let's say hydroelectric power generator, it converts mechanical energy to electrical energy. So a generator is also source. It converts mechanical energy to electrical energy. Okay. All right. So we've already used the symbol for a source, but let me give it again. The symbol for a source, for a DC source, symbol for a DC source is one long line, one short line. Okay. The long line is the positive terminal. The short line is the negative terminal. Okay. Now, let's define the EMF of the source. Electromotive force. Electromotive force, we are abbreviated by EMF. Okay. This is defined to be the work done by a source per unit charge to take charges from one terminal to the other. Okay. So what a source does is it takes charges from one terminal to the other. Okay. Let's say I have this one. Let's say we have this positive terminal, so it's going to take positive charges from this terminal to this terminal. Okay. So this becomes positive charge, it becomes negative charges. Now this takes the charges. This terminal is going to repel it. This terminal is going to attract it. So the external force has to do work to take the charge against their tendency. Okay, that's what a source does. It moves charges against their tendency. So naturally, they will go from positive to negative, but you're trying to build the charge over here. So as you build the charges, this charge will repel you, this charge will attract you. You're opposing the electric force. So this device, it has to do work to separate the charges. And the amount of work done per unit charge is called electromotive force. So this is work done by the source per unit charge. This is defined to be work done by the source per unit charge, per unit charge. Let me see. I think Vladislava, can you hear me? Let me see. This is...
Yes, sir.
Oh, okay. All right. Okay, so, this is work done by source per unit charge. So what I'm going to use E symbol for this one. This is going to be work done by the source per unit charge. This is the definition of electromotive force. Okay, so WS stands for work done by the source, work done by the source, and of course Q stands for charge. Okay, Q stands for charge. So this is the definition of electromotive force. And what is the unit? You see, this is joule per coulomb. You remember the unit for potential difference? Potential difference is change in potential energy per unit energy, right? That's joule per coulomb. So the same like potential difference, joule per coulomb. So the unit of EMF is also volts. Unit of EMF is volt. Okay. All right. Now let's have a source, let's say like this. Let's say it's MF is E. And then let's say this is connected to an external resistor. Okay, like this. All right. Now any source is going to have, is going to have its own resistance. We call that internal resistance. This resistance over here is the internal resistance of the source. Okay, any source will have its own internal resistance or internal resistance. Okay, we're going to use R3 represented. All right, so the potential difference that you get out of a source is not the entire EMF, it is the AMF minus a potential drop in the internal resistance. Okay, so let's say this is point A, let's say it's point B. The potential difference between points A and B, let's say delta V between A and B, is the EMF minus the potential drop in the internal resistance. So let's say suppose you have a current over here, and that potential difference is current times resistance. Okay, current times resistance. All right. So the potential difference available to the external resistance is this one, delta VAB, not the entire EMF. Okay. So you can say the potential difference across this resistor is also given by the same amount, which is current times resistance is also equal to this one. Okay. So this would be E minus IR. Okay. So we can use this formula to calculate the current in the circuit. All right. So we have EMF minus the potential drop in internal resistance equals I times R. We take, this is the other side, you've got I small r, I capital R equals current times R external resistance plus internal resistance. So you get the following formula for the current. The current is EMF divided by the external resistance plus the internal resistance. Okay, so you've got a battery of EMF E. You have to remember there is internal resistance in the battery. The current is not EMF divided by resistance, but EMF divided by the sum of the external resistance and the internal resistance. So that's how you calculate the current in. But if you know the EMF, you have also to know the internal resistance to be able to calculate the current. All right. Now let's look at rate of conversion of non-electrical energy to electrical energy, or let's say rate of production of electrical energy. Okay, rate of production of electrical energy, of electrical energy. Well, how does it produce it? It just converts non-electrical energy to electrical energy. Okay, so this basically power. So we're going to use PS. This is a power of the source. Okay, so the power of the source, if you remember, power is work divided by time, right? So this would be the work done by the source per unit time. Okay, now look at this formula over here. The work by the source equals EMF times charge. Okay, so work done by the source is equal to the EMF of the battery per unit charge, because the definition of EMF is work done per unit source. So the power, the power of the source is EMF times charge divided by T. Okay, now can you tell me what this represents as? Charge divided by time is rate of flow of charge. What's rate of flow of charge? Current, right? But charge divided by time equals current. Okay, so we have the following formula for the power of the source. It is EMF times current. Okay, so the rate of conversion of non-electrical energy to electrical energy is simply the product of EMF and the current. Okay, so this is the power of the source. The power of the source. It is the rate of conversion of non-electrical energy to electrical energy. This formula gives you how much energy is converted per second from non-electrical energy to electrical energy. All right. Now, suppose you have this source. Okay. So let's say we have internal resistance over here. This is R, and this is connected to an external resistance R. Okay. Now, the power produced by the source is current times the EMF. How about the power available to the circuit? The power available to the circuit is the power of the source minus the power dissipated in the interresistors. Okay, so power available to the let's see. Okay, the power available to the external circuit, that's called PR. Okay, PR, this is power available to the external resistance available to the external resistance, or R. Okay, it's not the entire power, EI. This is the power produced by the source, but some of it will be dissipated in the internal resistance of the battery itself, or the source itself, right? So you can subtract that. This is the power dissipated in the internal resistance. This is power produced by the source, okay? So the power available to the resistor is the difference between the power produced by the source and the power dissipated in the internal resistance. Of course, we just look at the resistor. This also should be equal to rate of dissipation of energy in the external resistance. So this is the power available from the source. And another way you can say that's also the power dissipated in the internal resistance. So these two expressions are equal, okay? So this is the rate of dissipation of energy in the external resistor, and current times current is the rate of production of energy in the source. And this one gives you the amount of energy dissipated in the internal resistance of the battery itself, okay? So let's consider an example. Suppose we have the following. Let's say this battery, let's say it has an EMF of, let's say, 10 volts, okay? Let's say this internal resistance is maybe 2 ohms. This is R, okay? And let's say this is our circuit over here. And let's say this internal resistance R, let's say, is maybe 98 ohms, okay? So first, let's calculate the current. A, let's say, calculate the current. Calculate the current, okay? If you remember, the formula for the current was EMF divided by external resistance plus internal resistance, okay? In this case, our EMF is 10, our external resistance is 98, our internal resistance is 2, right? So that's 10 divided by 100, 0.1 amps, okay? So the current in the circuit is 0.1 amps, all right? Now, B, let's say, calculate the potential difference between the terminals of the battery, Okay, so this is the EMF of the battery minus the potential drop across the internal resistance, okay? So that's what you have over here. You got the internal resistance over here. So we're looking for the potential in these 2 points. So that's EMF minus the potential drop in internal resistance, okay? So we're being asked for this, the potential difference between the terminals, maybe we type VAB, and that is the EMF minus the potential drop in the internal resistance, okay? So the EMF is 10, the current is 0.1, and the internal resistance is 2. So that is 10 minus 0.2, which is 9.8 volts, okay? So the voltage available to the external resistance is not 10 volts, but only 9.8 volts because of the potential drop in the internal resistance, okay? Now, this is also the voltage available to the external resistance, okay? So let's say calculate the rate at which, let's say, non-electrical energy, electrical energy is being converted to electrical energy. So what are we looking for over here? We're looking for the power of the source, PS, right? So, and that is simply current times EMF, all right? So the current is 0.1, okay? And the EMF is 10, all right? So that is 1. What's the unit of power? What's the unit of power?
Watt.
Watts, okay? So this is the rate at which non-electrical energy is being converted to electrical energy, all right? And now let's calculate the power available to the external resistor, say D, calculate the power available to the external resistance. Okay, so in this case, we're looking at this one, the power dissipated in the external resistance. So there are two ways of calculating it. Either you can use this formula, power produced minus the power dissipated in the internal resistance, or simply you can calculate it as the rate of dissipation of electrical energy in the resistor. Okay, these two are equal. So if you use this formula, the current is 0.1 squared, and the external resistance is 98. Okay, so that becomes 0.98 watts. Okay, all right. Okay, now we're going to look at a combination of resistors. You remember we looked at combination of capacitors. In this section, we're going to look at combination of resistors. Of course, we've done labs for series and power combination. So we're going to look at combinations of resistors. Combinations of resistors. So there are two kinds of combinations. Can you tell me what they are? We have two kinds of combinations of resistors. What do you call them? They're called series and parallel, right? So let's start with series combination. So we're going to look at series combination first. Series combination. So we say resistors are connected in series when they're connected in line, okay? We say resistors are connected in series when they're connected like this. This is series combination. When the resistors are connected in single line, they're said to be connected in series, all right? Now let me put the other page. So suppose let's say we have these three resistors, R1, R2, R3, okay? And they're connected to, let's say, potential difference delta V over here, okay? Now let's look at the defining properties of this kind of combination, okay? What can you say about the current through each resistor? They're on the same lines, so they're gonna have the same current, right? So the first defining property is that the total current is the same and the current through resistor 1, current through resistor 2, and current through resistor 3 because they're connected in series, okay? So the first property is the total current I equals current through resistor 1 equals current through resistor 2 and equals current through resistor 3, okay? Remember, our goal is to get a formula for the equivalent resistance. And second property has to do with potential difference. You see, this is the total potential difference between these two, but that equals the sum of the potential difference across R1, across R2, across R3, okay? So the second property is total potential difference equals delta V1 plus delta V2 plus delta V3, okay? Now let's define equivalent resistance. Equivalent resistance is the single resistance that can replace the combination without changing anything outside, okay? So you can define that to be, you remember, just like the equivalent capacitance is simply R equivalent capacitance equals total potential difference divided by the total current, okay? This is the definition of the equivalent resistance. Is the single resistance that can replace this combination without changing the current outside. Okay, so now let's use this formula to express this in terms of current. Okay, let me start from the second formula over here. So you've got delta V equals delta V1 plus delta V2 plus delta V3. Okay, so delta V is current times Req using this formula. Ohm's law is current times Req. This is the current, the same for all of them. Okay, so I'll just say current times R1, and this will be current times R2. This will be current times R3. Okay, so you see the current cancels out, right? So you get a formula for the equivalent resistance. The equivalent resistance is simply the sum of the resistors plus R2 plus R3, and there are more. The same pattern continues. Okay, so that's how you calculate the equivalent resistance for series combination. All right. So the most important thing over here is for series combination, all the currents are equal, and the total potential difference is the sum of the potential differences across the individual resistors. Okay, and the single resistance can replace the combination without changing anything, is obtained just by adding the resistances. Okay, now you remember the formula for capacitors. For capacitors, this was for parallel. Okay, so they flip. For parallel capacitors, you add them, but in this case, for resistors, you add them. So the two formulas, they flip for capacitors and resistors. All right. All right. Let's look at an example. So let's say we have the following circuit. Maybe let's say this is 6 volt, and we have these two resistors. Let's say maybe 2 ohm and 4 ohm are connected together like this. Okay. So we want to find the potential difference in current through the resistors. Okay. The question is calculate the current and potential difference through the resistors. Potential differences through the resistors. Across the resistors. Or through or across the resistors. All right. So we're going to simplify the circuit. We can combine these two by calculating the R equivalent, right? So R equivalent is simply the sum. So this is R2 plus R4. Okay, that is 2 plus 4. That is 6 ohms. So we can simplify this circuit in the following. We replace that one with Req. We have Req equals 6 ohms, right? And then our potential difference is 6 volt over here. So the current is delta V, total potential difference, divided by Req, right? So that is 6 volts divided by 6 ohms, and we get 1 amp. Okay, so the current in the circuit is 1 amp. Now we go back. Can you tell me what the current across these two resistors is? You see they're connected in series. It's the same current. All right. So this is I, but I equals I2 equals I4 equals 1 amp. Okay. So that we know the current passing through these resistors, and then we calculate the potential differences. So delta V2, the potential difference across the two resistors, is I2 times R2. Okay, that is 1 amps times 2, that is 2 volts. Okay, and the potential difference across the 4 ohm resistor is current times R4, which is 1 amp times 4, that is 4 volts. Okay, that's it. So you got the potential differences and the currents for each resistor. Now, if you want to check this formula, delta V equals delta V2 plus delta V4. Okay, this one is 6, and this are 2 plus 4. Okay, so checked, right? They go to 6. Check. All right. Now we're going to look at the second type of combination, which is a parallel combination. Number 2, parallel combination. Parallel combination. As you know, this is a branched combination, right? Resistors are said to be connected in parallel. They're connected like this. Okay, this is what you mean by a branched combination. Now let's call this maybe R1, R2, R3. Now suppose this is connected to a potential difference delta V over here. Now let's look at the properties of this kind of circuit. First, let's look at the potential differences. Can you tell me anything about the potential differences for parallel combination? Do you remember for capacitors? It's the same thing. So you see, there is no potential drop across a conducting wire because the resistance is practically zero, okay? So all these points over here are same potential. On the other side, all these points are same potential. So that tells you that this potential difference, this potential difference, this potential difference, this one are equal, okay? So the first property is the total potential difference equals to the potential difference across resistor 1 equals potential difference across resistor 2 equals potential difference across resistor 3, okay? So if resistors are connected, all the potential differences are equal, okay? How about the currents, okay? Now you have this current over here. What's going to happen? Some of it will go this way, that's I3. Some of it will go this way, that's I2. And some of it will go this one, that's I1, okay? So this current over here is branching into 3 currents. And the total current is the sum of all these currents, okay? So the second property is the total current is the sum of the currents across each resistor, okay? If there are more, the same pattern continues, okay? And our goal is to find a formula for equivalent resistance, all right? And equivalent resistance is total potential difference divided by the current, okay? So we're gonna use the second equation to do the derivation for the equivalent resistance. The second equation is total current equals I1 plus I2 plus I3 and so on, okay? Now current is total potential difference, total current divided by equivalent resistance, right? This I1, remember the potential difference are equal, so this is delta V. This is delta V divided by R1. This is delta V divided by R2. This is delta V divided by R3, okay? So delta V cancels out, so you get the following formula for the equivalent resistance. Is 1 over R1 plus 1 over R2 plus 1 over R3, so on. Okay, so that's how you calculate the equivalent resistance of resistors connected in parallel. You remember, for the case of capacitors, this was for series. Okay. All right. Well, if you want, you can write this one as follows. Maybe this is easier to use in a calculator: 1 over R1 plus 1 over R2, and so on to the power of -1. Okay. Now, this is a cumbersome formula, but for 2 resistors, we can simplify it. For 2 resistors, we have 1 over R equivalent equals 1 over R1 plus 1 over R2, okay? And then this one multiple, we got R1, R2 over here, we got R1 plus R2 over here, and then we get the following formula for REQ. REQ is product over sum. You got inverted because it's inverse. So this is simply product over sum, okay? But remember, this formula doesn't work if you have more than 2 resistors. This applies only for 2 resistors. If you've got more than 2 resistors, you got to use the original formula, okay? So let's look at an example. Suppose we have this, let's say the 6-volt battery, and then we have these 2 resistors. Maybe let's say we have the same resistances, 2 ohm and 4 ohm over here. Okay. Now we want to calculate the potential difference in the currents through each resistor. Okay. The question is calculate the potential difference and current in each resistor. Okay. Now, can you tell me what the potential differences are? What are the potential difference across the 2 ohm and 6 ohm resistors?
So if the potential difference remains constant?
For parallel combination, all the potential differences are equal, right? this purport over here, all the potential differences are equal, right? So we'll just say delta V2, delta V4 equals total potential difference equals 6 volts, okay? They're equal because they're connected in parallel. Now for the current, I2 is delta V2 divided by R2. All the potential differences are the same, so we've got 6/2. That is 3 amps, okay? And then I4 will be delta V4 divided by R4, okay? And that is 6 divided by 4, and that's going to be 1.5 amps, okay? Now, if you want to calculate another way, you can calculate the equivalent resistance first. Let's calculate the equivalent resistance. So Req is, how do you calculate Req? It's product or sum, right? So it will be R2, R4 divided by the sum of the resistors, okay? So it'll be 2 times 4 over 2 plus 4, that's 8/6, or 4/3 ohms, right? And from that, of course, you can calculate the total current. The total current is delta V divided by Req, right? So that is 6 divided by 4/3. That's 18/4, or 9/2, or 4.5 amps, okay? So it's total current. But you can also calculate total current by simply adding the currents, I2 plus I4, right? And we already calculated this one's over here. So we have one of them is 3, one of them 1.5. So you got 3 plus 1.5, you get 4.5, okay? So you get the same thing either way, all right? So this is these two special combinations, series and parallel. But sometimes you can have a combination of parallel and series in a circuit. So let's demonstrate this by means of some examples, okay? So let's say parallel series combinations, parallel series combinations. Okay. Oh, she doesn't get it. All right. Okay. So first, let's look at an example for calculating equivalent resistance. We've done for capacitors, but we'll do. Okay, let's say each is 2 ohms. Let's say each resistor is, let's say, a 2 ohm resistor. Okay. So let's say we have the following circuit. Maybe we have the following over here. Maybe we have like this over here. Maybe another one like this. Okay, they're all 2 ohm resistors. The question is to calculate the equivalent resistance. Okay, so what you can do is you can simplify it by combining those resistors that are in series or in parallel. All right. So first we can combine these two. They're in parallel, right? So what's the equivalent resistance for these two? They're 2, it's product over sum, right? So this will be 2 times 2 over 2 plus 2, which is 4. This can be replaced by 1 ohm. The same thing over here. 2 times 2 over 2 plus 2, this also can be replaced by 1 ohm. How about this? This is sum, because they're in series, right? So I can simplify this one into the following. So there's still 2. Now we can replace by 1. The equivalent resistance is 1. It's also 1. Okay? And then this is, they're in series, 2 plus 2, that's 4, right? So I've got 4 over here. And then I got another 2 over here. All right. Next, what can I do? I can add these two. Okay, they're in series, right? I can further simplify it. So I have the following. I have this 2, okay? And then I combine these two. They're in series. I simply add them. It's 1 plus 1 equals 2. All right. So I get this one over here, this one resistor, which is 2 ohm resistor. And then I have a 4 ohm resistor over here, okay? So I've got a 4 ohm resistor over here, all right? And then finally I've got this 2 ohm resistor, all right? Now I have these two in parallel, okay? In parallel is product over sum. So for this, I can use 2 times 4 over 2 plus 4, which is 8 over 6 or 4 over 3. Okay, so finally I have the following. I've got these two. I've got now this, the equivalent resistance of these two, which is 4 over 3, and then I've got the 2 over here. Okay, now finally I've got 3 resistors connected in series, right? So I got to use the general formula. So the general formula is 1 over Req equals 1 over 2, 1 over 4 over 3, and then plus 1/2. Okay, half plus half is 1, and this will be inverted, 3 over 4. Okay, this is 4 over 4, so you get 7 over 4. So the equivalent resistance for this combination is 4 over 7 ohms. Okay, so the main idea is if you've got a combination that involves parallel and series, simplify it step by step by combining those in parallel and in series. All right. And now let's look a circuit containing parallel and series. All right, maybe we'll put it on the other side, on the other page. Suppose I have the following circuit. Example. Let's say we have this potential difference, let's say 6 volt over here, but then we have, let's say, 2 ohm over here, maybe 1 ohm over here, maybe 2 ohm over here, maybe let's make 3 ohm and 2 ohm. Okay, the question is, calculate the potential difference and current in each circuit. Okay, the question is calculate the current and potential difference of each resistor. Potential difference of each resistor. Okay, so we're going to simplify the circuit. The first simplification we can do is we combine these two. They're in parallel, right? So we can combine 1 and 3. Let's call this R1. Let's call this R2. Let's call this R3. Okay, so the combination of 1 and 3, they're in parallel, is product over sum, right? R1, R3 divided by R1 plus R2. That's going to be 1 times 3 divided by 1 plus 3, which is 3 over 4. Okay, so this can be simplified the following. We can replace this one by 3 over 4. Okay, so we have this simplification now. We still have a 2 ohm over here. This one now, I've combined these two. So that's R13, and that is 3 over 4. 3 over 4, all right? Then we have this one, all right? And this is still 6 volt over here. Again, we can simplify it. These are in series, so the equivalent resistance is the sum, right? So I can simplify this. This is R equivalent now is 2 plus 3 over 4, okay? Or 11 over 4. That's my equivalent resistance. So this simplifies to the following circuit. So you have a single resistor, which is the R equivalent, 11 over 4. Okay, you got 6 volts over here. Now we can calculate the current, right? Let's calculate the total current. So the total current is total potential difference divided by Req, right? The total potential difference is this one, 6 volts, right? So delta V is 6 volt, and Req just calculated it. So it's going to be 6 divided by the equivalent resistance, which is 11 over 4. Okay, so divided by 11 over 4, and that is 24 over 11 amps. Okay, now let's go back. The current over here is 24 over 11, right? What do you think is the current over here? The same thing. These two are connected in series, right? So you have the same current as this one, all right? So the current across 2 and the current across 1, 3 are the same, and they're equal to this one. So you can say that the current across the 2 ohm resistor, the current across the combination of 1 and 3 equals the total current equals 24 over 11 amps. Okay, moving backwards, all the currents are equal because they're connected in series. Now we can calculate the potential difference across this one, across this resistor over here. See, this one, which is this one over here. Okay, so delta V2 is I2 times R2. Okay, so you've got 24 over 11 times the R2, which is 2, right? So you get 48 over 11 volts. Okay, that is the potential difference across this one. So for this one, we have both the current and the potential difference. Now let's go back over here. Okay, let's calculate the potential difference across this one, because we know since these are connected, the potential difference are the same. Okay, so let's calculate the potential difference across the combination of 1 and 3. That is the current across 1 and 3 times the equivalent resistance of 1 and 3, right? The current is 24 over 11, so over here. What was the equivalent resistance for 1 and 3? This is the combination, which is 3 over 4, right? So this times 3 over 4, 3 over 4, all right? So this goes 18 over 11, volts. Okay, now look, this one, R13 over here, is the combination of these two, the parallel combination of these two. So the potential difference across this one and these two are the same. Okay, so we go back, we say the potential difference across 1 equals the potential difference across 3 equals the potential difference across their combination equals 18 over 11. Okay, now you can calculate their currents. I1 is delta V1 over R1. Okay, so that's 18 over 11 divided by 1, which is 18 over 11 amps. And I3 is delta V3 divided by R3. Okay, delta V3 is 18 over 11. Okay, and then you divide that by 3. So we have 18 over 33 amps. So you see, the problem is complete. We got the currents and the potential differences for each resistor. So the main thing is first you should simplify. These two are parallel. You combine them together, we get this combination. So you've got a series combination of these two and this, which is parallel combination of these two. And then we further simplify. We find the equivalence of these two, and then we finally get a circuit with one resistor. Okay. So from that, you can calculate the current from this circuit. When you go back, these two, so they're in series, they're going to have the same current, okay? So you have the current for this one, the current for this one. You calculate the potential difference for this one, and then you go back, since these are connected in parallel, they're going to have the same potential difference, okay? So that way you can solve for everything, all right? Now, but sometimes you have circuits which are neither series nor parallel. So how do we deal with these kinds of problems? We have rules that we call Kirchhoff's rules. So we're going to look at Kirchhoff's rules. Kirchhoff's rules. These rules are used to solve complex circuits, okay? These are used to solve complex circuits. There are two of them. They're called the junction rule and the loop rule, okay? So let's look first at the junction rule. Number one, the junction rule. The junction rule. First, let's state what a junction is. A junction is a point where one or more wires meet, okay? This point over here is a junction. It's a point where one or more wires meet. Okay, so what does this rule says? It says the sum of all the currents in a junction is 0. Of course, the same convention. Let's say we call this one I1. Let's say we call this one I2. Let's say we call this one I3. If you use the same convention that what comes in is positive and what comes is negative, or what comes out is negative, then obviously you see what comes in equals what comes out. Okay, so when you add them, you get a 0. This is a very simple rule. It simply says what comes in equals to what comes out. That's all it says. Okay, so this junction rule says the sum of all the currents in a junction is 0. This rule says that the sum of all currents in a junction is 0. Okay, that is the summation of all the currents in a junction equals 0. But let me write the sign convention. The sign convention Okay, current that comes in is taken to be positive, and current that comes out is taken to be negative. Current that comes in, that's to the junction, or comes out is taken to be positive, and current that comes out is supposed to be negative. Okay, so in this case, this current will be positive because it's entering the junction, but these two currents will be negative because they're leaving the junction. Okay, the sign rule. But in applying this formula, it's better to assume these variables represent positive numbers. Okay, you will see later why that's important. Because to start with, you don't know what the direction of the current is. So the sign of the current can tell you which way the current is going. So we're going to assume these symbols represent positive numbers. For that reason, I'm going to rewrite the summation as follows. Assuming the variables represent positive numbers, I'm going to write the law as follows. So if you assume the currents are positive, then you have to put plus or minus I over here equals 0. Or if you extend it, you can say plus or minus I1 plus or minus I2 plus or minus I3 and so on. Okay, equals to 0. And then you pick the plus or minus depending on the same convention. If it's coming in, if it's going in, you pick the plus sign. If it's going out, you pick the minus sign. Okay. So we're going to write the law as follows. So we're going to assume the variables are positive, and then we introduce the negative and positive signs outside. Okay. Now let's apply this rule to this one, to the one we've already. So let's say I1 is going this one. Okay. Let's say I2 is going this way. Let's say I3 is going this way. Okay. So is I1 positive or negative? It's going in.
Positive. Positive.
Positive. So we're going to pick the plus sign for I1. Okay. This one is leaving. I'm going to pick the minus sign. This one is leaving. I'm going to pick the minus sign, and then equate to 0. Okay. So it's basically what this is. What comes in equals what comes out. That's all we're saying. Okay. It's a very trivial law. What comes in equals what comes out. Okay. So this is the junction rule. And the other thing you have to know about this junction rule is if you have more than one junctions, let's say if you have n junctions, you have to apply the junction rule only to n minus one of them, because the nth one is not an independent equation. Okay, if there are n junctions, apply the junction rule to n minus one of them. To n minus one of them. The reason is the n minus one is not independent. That is, the n's equation is not independent. Equation is not independent. Okay, you'll just get a redundant equation. For example, let's consider a case where you have two junctions like this. Let's say we have in this equation, in this circuit, we have two junctions over here. Okay, let's say the current going this one is I1. So remember, this is one wire. So this is I1, this is I1. Okay, and then let's say this one is I2. Remember, this is one wire. This is all I2 over here. And let's say it's I3. Okay, so let's apply the junction rule over here. What do we get? We get I1 minus I2 minus I3 equals 0. Now let's use this one. Now you see I1 is coming out. So that's negative. Okay, but I2 and I3 are coming in. Okay, so all it did was just multiply this equation by a negative. It's an identical equation. It's not an independent equation. Okay, so if you apply the junction rule to all of them, the last one is not going to be an independent equation. It's going to be a dependent equation. So if you have n junctions, you just apply to n minus one of the junctions. Okay, so that's the junction rule. Next, we're going to look at the loop rule. The loop rule. the loop rule. This rule says the sum of all potential differences in a loop is 0. The sum of all potential differences in a loop is 0. Okay, so if you add up all the potential differences in a loop, in a complete loop, you should get 0. Okay, but let me distinguish between two kinds of waves, of loops. If you've got a non-intersecting loop like this, it's called a simple loop. Okay, a non-intersecting loop. This basically means a non-intersecting loop. A non-intersecting loop. Okay, but this one is not simple. Okay, so we're going to see we have to apply this rule to simple loops. Okay, so that's what we meant. For example, in this case, you see over here, this is a simple loop. This is a simple loop, but this one is a loop, but it's not a simple loop. Okay, one of the rules is you have to apply the loop rule to the simple loop. So that's what by simple loop. Simple loop is a non-intersecting loop. Okay, now this is a very simple equation, but we have to be careful with the signs. So let's look at the sign convention. Sign convention. That is when to make them positive, when to make them negative. Sign convention. Sign convention. As you know, there are two kinds of potential differences in a circuit. You've got devices that convert non-electrical energy to electrical energy, the source, just like a battery. And you've got devices that convert electrical energy to something else, that's a resistor. So we're going to have two different conventions for both of them, okay? So let's start with a battery, or generally the source, okay? Let's start with the battery. Suppose you have the following battery. But first, let me define what we mean by transverse interaction. Now, let's say you have this circuit over here like this and so on, okay? What this rule says is you add up all these potential differences and you get 0. But it doesn't matter which way you add them, but you have to decide which way to add them. You can start this one, you can add them in a clockwise direction and counterclockwise direction, or you can add them in a clockwise direction like this. It doesn't matter which one you pick, but you have to decide which way you want to go. Because the reason is the sign convention depends on these directions, okay? So these are called transversing directions, either clockwise or counterclockwise, transversing directions. That is, you have to decide whether you want to add them in a clockwise direction and a counterclockwise direction, okay? Because the sign convention depends on those directions, okay? So let's look at a battery. Now, suppose you're transversing this battery in this direction. Okay? So you're going from positive to negative, it's decreasing, right? So the potential difference is negative for this one, right? But if you transverse it in this direction, from the negative to positive, the potential difference is taken to be positive. You see that? These are transversing directions. For example, for this one, if I'm adding this way, you see, I'm going from positive to negative, this will be negative. But if I come this way, I'm going from negative to positive, will be positive, okay? That's why transversing direction is important, because the sign conventions depend on which way you're going, okay? So if you're going this way, this would be negative because it's decreasing. If you go this way, it will be positive because the potential difference is increasing, okay? So that's the sign convention for a battery. If you transverse it from the positive to the negative, you should take it to be negative. If you transverse it from the negative to positive, you should take it to be positive, okay? Next, let's look at a resistor. Okay? Suppose we have this resistor over here. Now, the sign convention depends on the direction of the current, okay? Let's say the current is going this way, all right? Now, what happens when charges cross a resistor? They lose potential energy, right? Some of the energy is converted to heat energy. So what happens is this point over here will be a lower potential than this one because the charge lose energy if they cross it, okay? So if you transverse it this way, you're going in the direction of decreasing potential difference. So you take it to be negative. This is the direction of current. This is the direction of current, this is transversing direction, okay? So if you go this way, you go in the direction of a negative or a decreasing potential energy. So you take it to be negative, okay? But if you transverse it this way, you're going in an increasing potential energy direction, you take it to be positive, okay? So for a resistor, it depends on the direction of the current. If you go in the direction of the current, it is negative. If you go opposite to the direction of the current, it is positive, okay? So this sign convention is very important when we solve problems like this. So first you have to pick which way you want to go, clockwise or counterclockwise. So these are the transverse directions over here. If you cross it this way, this will be negative. If you cross it from negative to positive, it will be positive, all right? For resistor, if you're going the direction of the current, you're going the direction of decreasing energy, you take it to be negative, okay? But if you go the other way, opposite direction of the current, you take it to be positive. And remember, the potential difference of a resistor is current times resistance. All right, so these are the sign conventions. So let's start with a simple circuit. Example, let's solve a very simple circuit. Suppose we have the following circuit. Let's say maybe this is 6 volts. We have a resistor over here, let's say it's 5 ohms. Maybe another one over here, let's say it's 10 volts. And then another resistor over here, let's say it's 10 ohms. Let's say it's what we have. Okay, now, before you start, you have to assume a direction for the current. We don't know which way is going right now, okay? But you don't have to know. You remember we said we're gonna assume the current is positive, all right? So you pick any direction, either clockwise or counterclockwise. If your answer is positive, that means the direction you chosen was right. If your answer is negative, the direction is opposite direction you've chosen, okay? So you don't have to know the direction of the current beforehand. The answer will tell you. You pick any direction. If your answer turns out to be positive, then the assumed direction was correct. If your answer turns out to be negative, your assumed direction was wrong. You have to reverse it, okay? So let's assume the car is going this way. This is just an assumption, okay? We don't know which one is going. The answer will tell which way is going, okay? Now, we don't have junctions over here. We just apply the loop rule, okay? For the loop rule, we have to add up all the potential differences and equate them to 0. So you have to decide where you want to start. Let's say start over here. And then you have to decide whether you want to go clockwise or counterclockwise, okay? Maybe let me go in a counterclockwise direction like this, all right? So let's do it. I'm going to apply the loop rule. I'm going to add all the potential differences and add them together, okay? So the car is going this way. I'm going opposite direction of the current. Do you think this will be positive or negative? If you go opposite to the direction of the current for resistor, if you go opposite to the direction of the current this way, it's positive. If you go the same direction, it's negative, okay? So this potential difference over here is positive because I'm going opposite to the direction of the current. I'm going this way, but the current is going this way, okay? So the potential difference for that resistor is 10I. How about this one? I'm going from positive to the negative. Do you think it will be positive or negative? If you go from positive to negative, it is negative. You see, if you go this way, from positive to negative, it is negative. So this would be minus 10. Minus 10, okay? We keep going, we encounter this resistor over here. We're still going opposite direction of the current, going this way, but the current is going this way. So it's going to be positive, okay? That's 5 times I, okay? I keep going. Now I'm going from positive towards the negative. This is also negative, okay? Because I'm going from positive to negative, right? So it's going to be minus 6. I come back to my original point. I have added up all of them. I equate this to 0, okay? So I've got 15 I's, and then I've got 11 on the other side, okay? So my current is 11 over 15 amps. So it turned out to be positive. What does that mean? My assumed direction is correct. The current is actually flowing in a clockwise direction, okay? So the direction of the current is clockwise. My assumed direction was correct. But if this one turned out to be negative, it means the current is flowing in the other direction, okay? So you don't have to know the direction of the currents beforehand. The answer will tell you which way. If your answer turns out to be positive, your assumed direction is correct. But if the answer turns out to be negative, the direction is the other way around. If you choose clockwise, it will be counterclockwise. If you choose counterclockwise, it will be clockwise. Okay. All right. So this is a very simple circuit. Now we're going to solve a problem with 2 loops. Okay. Another example is 2 loops. So let's solve maybe this circuit. Let's say we have this one over here. Maybe we have another resistor over here. Potential difference over here. Maybe another resistor over here. Another battery over here. Maybe another resistor over here. Okay. Then put maybe battery over here too. Okay. So let's put some voltage over here. Let's say 6 volt. Let's say 10 volt. Let's say 2 ohm. Let's say 6 ohm. Maybe 10 ohm. Okay. Now let's go through the process you need to go through to solve this equation. Number 1, the first thing you have to do is assign directions for the currents in all of the wires. How many wires do I have over here? Can you tell me? How many wires do I have in this circuit? I have 1 wire, 1 current for that wire. I have this wire, another current for that wire. I have this wire, another current for that wire. I have 3 wires. So that means I'm going to have 3 currents. Okay. So the first thing you have to do is assign a variable and direction for the currents in each wire. Current is in each wire. So in this case, I have 3 wires. I'm going to have 3 currents. Okay. So let's do it this way. Let's say this is my I1 over here. Okay. It's just an assumption. I don't know which way they're going. Okay. So let's say this one over here is I2. Let's say this one is I3. Okay. So I've done that. I've assigned directions and variables I1, I2, and I3. Can you see that this one is I2, I2, okay. I2, I3. All right. Okay. Once you do that, if there are n junctions, apply the junction rule to n minus 1 of them. Okay. If there are n junctions, apply the junction rule to n minus 1 of them. So how many junctions do I have in this circuit? Can you tell me? How many junctions do I have?
2.
There's one over here. Do you see another one? This one. I have 2. So I have to apply the junction rule only to one of them. Okay. The other one is going to be a redundant equation. I'm not going to get any information from it. All right. Okay. So let's do that. This junction. I have 3 currents. So this is my equation: plus or minus I1 plus or minus I2 plus or minus I3 equals 0. Right. Now let's pick the signs. If it is going in, it's positive. It's going out, it's negative. Okay. So I1 is positive, but I2 and I3 are negative. Okay, equals 0. Now we have 3 variables over here. That means you need 3 equations to solve this problem, but we can eliminate one of the variables right in the circuit. Okay, let me take I3 the other side. So I've got I1 minus I2 equals I3. Okay, instead of dealing with 3 variables, what I can do is I can replace this right in the equation. Instead of I3, I'm going to put I1 minus I2. Okay, so that I have to deal only with 2 equations. You see, so in the circuit I have replaced I1 minus I2. So now apply the loop rule. I'm just going to have 2 variables, I1, I2, because I replaced it with I1 minus I2. Okay, so the easiest thing to do is just eliminate one of the variables right in the circuit. Okay, that reduces your equations from 3 to 2 immediately. Okay, so that's junction rule. And then we go to the loop rule. The third rule The third rule is apply the loop rule to all of the simple loops. Apply the loop rule to all of the simple loops. Okay, so how many simple loops do I have? Can you tell me? In this circuit, remember, a simple loop is a non-intersecting loop. We have 3 loops in this circuit. We have one over here, we have one over here, and then we have a third one over here. Which ones are simple? Just this one and this one. Okay, this one is not simple because an intersecting loop. All right, so I just have 2 simple loops. Let's call them A and B. Okay, I have 2 simple loops. All right, okay, and then assign transversing directions. It doesn't matter which way you're going, it will be clockwise or counterclockwise, but you have to assign it. Okay, assign transversing directions for all of the simple loops. For all of the simple loops. Okay, so I have 2 simple loops over here. I'm going to assign transversion direction. It doesn't matter which way, but I need to choose. Let's say I decided to go counterclockwise over here. Maybe I decide to go clockwise over here. Okay, so now we're going to do that for loop A and loop 2. We're going to apply the loop rule to loop A and loop B. So let's start with loop A. Okay, now it doesn't matter where you start, but you have to decide where you want to start. Okay, so let me start over here. I have to go all the way around and come back over here to equate to 0. All right, so I1, which was I1 going? Means I1 is going this way, right? So when I cross this resistor, I'm going opposite to the direction of the current. So this potential difference should be positive, okay? And the current is I1, all right? So my first potential difference is from Ohm's law, 6 times I1, and it's positive, okay? I'm crossing this resistor now. All right. Did I say 10 ohms for this one? Oh, that's 10 volts. Let me give maybe 8 ohms for this one. Okay, I don't think I stated the resistance. Okay. All right. So after that, I encountered this resistor over here. Okay. This resistor is 8. The current I2 is going this way. Okay. Now also I'm going opposite to the direction of the current, right? You see that? I'm transversing this direction, but the current is going the other way. So this potential difference is also positive, okay? And the current is I2 in this wire. So it's going to be plus 8 I2, plus 8 I2, okay? All right, after that, what do I encounter? I encounter this battery over here, which is 10 volts, okay? This will be positive or negative. I'm transversing it from the positive to the negative. This will be positive or negative. If you go from the positive to the negative, it is negative, okay? So this 10 volt is going to be minus 10. So this potential difference over here will be minus 10, all right? All right, I'm here right now. I keep going, I encounter this resistor. For this resistor also, I'm going opposite to the direction of the current. I'm transversing this way, the current is going this way. So it's going to be positive, okay? That is 2 times I1, the current is I1. All right, so I've got plus 2 I1. All right, I keep going. I get this battery over here. For this battery, I'm crossing it this way, from negative to positive. This thing will be positive or negative? If you go from negative to positive, it is positive, okay? Basically, the potential difference is increasing. So this is going to be plus 4. This is going to be plus 4, okay? Now, after that, I come back to where I started. I've added all of them, I equate to 0, all right? So this is equal to 0, okay? So let's simplify it. We've got how many I1? We got 8 I1. we've got 8i2, 8i2. And from the numbers, minus 10 plus 4 is negative 6, so you get 6. So we have this equation, okay? Maybe we can divide by 8. You get I1 plus I2 equals 6 over 8 or 3 over 4. So that is my first equation, but I have two variables. I cannot solve it with a single equation. I'm going to another equation. Where do I get the other equation? I get it from loop B, okay? So we're gonna do the same thing for loop B. Loop B, okay? So we've decided to go this way for this one, and it doesn't matter where you want to start, but let's say we start over here, okay? And I'm going this way. When I go this way, this is the first resistor I encounter. Now look, the current's going this way. See that? And that is in the same direction as the transversing direction. So this one is going to be negative. Now instead of I3, I'm going to use I1 minus I2, okay? Because we decided this is equal from the junction rule, okay? And it's negative because I'm going in the direction of the current, okay? So it's going to be minus 10 times the current. Minus 10, and the current is I1 minus I2. All right. Okay, let's keep going. All right, I'm going this way. And then I find this resistor. For this resistor, you see the current's going this way, but I'm going this way, right? Opposite. So it's going to be positive. If you go opposite to the direction of the current, it's going to be opposite. Okay, so it's going to be plus 8, and the current is I2. So you've got plus 8 times I2. Okay. All right, now I'm here. Now I get a battery over here, which is 10 volts. I'm going from the positive to the negative. When you cross a battery from the positive to the negative, it's negative, okay? So that's minus 10. So I've got minus 10, all right? Okay, now I've got this battery. I keep going. I encounter this one. For this one, I'm going from the negative to the positive. This is going to be positive, okay? That's plus 6. Plus 6. All right? And then finally, I'm where I started, okay? So I've added all of them. According to the Kirchhoff's loop rule, I equate them to 0, okay? So this is 0 over here, all right? Now we can simplify it. You've got negative 10I1 plus 10I2 plus 8I2, and then this is minus 4, let's say equals 4, okay? So we have negative 10I1, and then we have 9I2. 9I2 equals 4, okay? So we have two equations now. Let's put them together. We have I1 plus I2, I1 plus I2 equals 3/4. Okay, and then we have negative 10I1, negative 10I1 plus 9I2 plus 9I2 equals 4. Okay, so this is a system of two linear equations. So there are two ways you can solve it. Either you can use the method of substitution, or you can use method of elimination, whatever you feel comfortable with. Okay. In either case, you're trying to get a single equation in one unknown. Okay. For substitution, you can replace I1, use the equation over here. Okay. Or for elimination, you can add this two in such a way that all the variables go away. You can multiply it by 10, and then when you add this one, go away. But let's say substitution. Let's say, because most of the time substitution is easier in this case. These numbers look good, but most of the time these numbers are not going to be, they're going to be fractions and stuff. Okay, so elimination is not going to be useful with this kinds of numbers. So let's do it with substitution. So this would be 3/4 minus I2, right? And then instead of I1, I put this in this equation, right? So I've got negative 10, and then I've got 3/4 minus I2 plus 9i2 equals 4. Okay, so now I have only one unknown. I can solve it. Okay, I don't know if I should go through it. This is negative 15 over 2 plus 10i2 plus 9i2 equals 4. So you've got 19i2 is 4 plus 7.5, which is 11.5. 11.5. Okay, so I2 turned out to be positive. Okay, this is 11.5 divided by 19. Okay, so what does the fact that it's positive tells me? You see, this was just an assumption. We assumed the current was going this way, but the fact that it's positive tells me my assumption was right. So I2 is actually going this way. Okay, so we have I2, and then you calculate I1 from here. I1 is this 0.75 minus this thing, 11.5 over 19. The same positive or negative. It looks like nothing's positive, right? So that means I1 is the same direction, and then you calculate I3 from I1 minus I2. Okay, and that completes the problem. So if your answer is positive, your direction or your assumed direction is correct. If your answer is negative, your assumed direction is wrong, you reverse it. Okay. Now we just applied it for 2 loops over here, but these rules work for any loops. Even if you have 10 loops, the only difference, you might have 10 by 10 equations, but you can still solve it. It's using a computer, you can solve any complex circuit. Okay. The number of equations will be equal to the number of loops, but you can solve any system of linear equations with a computer or Cramer's rule. Okay, so these 2 loops, they help you to solve any complex circuits. Okay, all right. Now we're going to look at a circuit where a battery is connected to a resistor and a capacitor. Okay, so let's say a battery connected to a resistor and a capacitor, to a resistor and a capacitor. Okay, so we're going to study the circuit. So let's say you have this battery of EMF E, and then you have, let's say, a resistor over here and a capacitor over here. These 2 lines equal. Okay, we want to study this kind of circuit. Okay, so in this case, obviously, the current will go this way. Remember, even though it's electrons that carry charge, conventionally, we assume currents are carried by positive charge. So the direction of the current is going to be this way. Okay, so let's apply Kirchhoff's rule to this equation. Let's try to go this way. Okay, so if I start from here, first I get the battery, that's the EMF. When I come to the resistor, I'm going the direction of the current, it's going to be negative. It's minus current times resistance. And this also is going to be positive, this is going to be negative, and when I cross, it's going to be potential drop. That's also going to be negative, okay? And the potential drop across the capacitor is charge divided by capacitance, okay? Now I'm back to where I started, equals 0. So this is the equation we have to solve. All right, now remember, current is the derivative of charge with respect to time, okay? So this equation becomes current minus the derivative of charge with respect to time times resistance minus charge divided by C equals 0. So it's going to be a differential equation. This is first order differential equation. When you solve differential equations, the first thing you should check is if you can use the method of separation of variables. Have you dealt with, I think, so in this case, you can use the method of separation of variables, okay? But let me Well, first I realize this one. The multiply negative, so you've got dq by dt times the resistance plus q over c, and then minus e equals 0. Okay, so let's divide by r, the whole equation. Okay, so you get the following. When you solve a differential equation, it's easier to make the coefficient the first, the highest order derivative to 1. Okay, so we have this one, the derivative of charge with respect to time, and then we have q over rc plus q over rc, and then minus e over r equals 0. Okay, so we're trying to separate the time and charge variables. Okay, so I'm going to take the other side. So we're going to say dq over dt equals, let me take this on the other side, so it's going to be e over r minus q over rc. Okay, then we can multiply by dt. You will say dq equals e over r minus charge divided by rc times dt. Okay, we're trying to separate the time variable and the q variable. So if I divide this by the whole equation, remember, these are constants. My variables are q and time. See what's going to happen? The charge will keep building up in the capacitor. Okay, so the charge in the capacitor will keep increasing as it gets charged. All right, so my variables are time and charge. So I can divide this by this whole equation, separate q on one side. So you've got e over r minus q over rc equals dt. Okay, now I've separated my variables. I have only q on one side, I've got only time on one side. My variables are charge and time. Okay, so we can integrate now. We can integrate this. So the time obviously goes from 0 to t. How about the charge? You see, we're starting with a 0 charge for the capacitor, but eventually we'll keep building charges. Okay, so the charge starts from 0 and then the charge as a function of time. Okay, this is our integral. All right. All right, so this is obviously t. All right, now we have to use method of substitution. So I'm going to say let u equals, I'm going to substitute by u. Okay, so that's EMF divided by resistance, charge divided by RC. Okay, so what's du? The derivative of this one is 0, right? And so we just get negative 1 over RC times dq. Okay, so I'm trying to search for dq. So dq is negative RC times du. Okay, so I'm going to use this substitution for dq. Okay, I'm going to replace dq by this one. I'm going to replace this by u. Now let me substitute my initial and final values. Okay, so when q equals 0, what does u become? Okay, well, let me write u over here. So we have u equals e over r, u equals EMF divided by resistance, and then we have charge divided by RC. Okay, charge divided by RC. Okay, so u at q equals 0. This is just e over r. Okay, and u at q is simply the same thing, u over r minus q over rc. All right, so the integral becomes as follows. Okay, the u goes when q is 0. This is e over r. For arbitrary q is e over r minus q over rc. Okay, how about dq? dq is dq is negative rc du, right? So we have negative rc du, and then we just replace that by u. Okay, and that equals time. This is over here, this time over here. So this is our equation. Okay, maybe let me take the rc to the other side. So we get the following: the integral from e over r and then we've got E over R minus Q over RC equals, I'm going to take the constants the other side, minus Y RC T. And this is du over U. What's the integral of du over U? What's
Log
the integral of 1 over x?
natural log of u.
Ln, right? So this is ln of U going from E over R, and then E over R minus Q over RC equals negative 1 over RC T. Okay? So this becomes ln. The minus would be a ratio, it's a logarithm, right? So E over R minus Q over RC, E over R minus Q over RC divided by E over R equals negative 1 over RC T, right? All right. What did I do? All right, okay. So I'm going to change this to exponential right now, okay? So I have the following, E over R minus, remember we're trying to solve for Q, okay? QRC divided by E over R equals E is the power of negative 1 over RC times time, okay? I just changed the ln to an exponential function. So you've got E over R minus Q over RC equals EMF divided by resistance, and then E negative 1 over RC times T, okay? So that tells me Q over RC is E over R minus E over R, E negative 1 over RC T, okay? So we can factor out this one, E over R, you get 1 minus E negative 1 over RC times time, okay? And then, of course, R cancels out, right? So I have the following. Q as a function of time, we can cancel R over here, is capacitance times EMF, and then 1 minus E negative 1 over RC T. All right, so that's how the charge varies as a function of time. You see that? Is everybody here? Can you hear me? Since we got 4 participants, I don't. All right. So this is the final charge. You see what happens over here? We start with 0 charge, but at t equals infinity, this ends up to be the charge accumulated by the capacitor. Okay, so let's study the property of this function. At t equals 0, what's the value of this exponential at t equals 0? E to the power of 0 is 1, right? So q at t equals 0 is simply 0, 1 minus 1, okay? So q, that's actual or assumption. We assume the charge is 0 at t equals 0. So you've got q at t equals 0 is actually 0. Now let's take the limit of this as t approaches 0, as t approaches infinity, okay? Let's do this. The limit of the charge as t approaches infinity, okay? So it's going to be the limit as t approaches infinity of this one, EC, and then you got 1 minus E negative 1 RC T, okay? What's the limit of this exponential as t approaches infinity?
0.
What did you say?
0, because it'd be e to the
Yeah,
negative
this will go 0. Very good. So this goes to 0. So it just becomes E times C. Okay. So this would be the charge of the capacitor at infinity. So it starts from 0, and at infinity it approaches this value. So now we can plot the graph. It's an exponential function. Okay. We just saw that t equals 0 is 0, and this is EMF times the capacitance of the capacitor. Okay. So it approaches to this value as we go to infinity, okay? So the charge builds up slowly to this value, okay? So that's how the charge increases in this circuit. All right, how about the resistor? Well, the resistor is current times resistance, right? So let's do the current first. What's the current? Current is dq by dt, right? It's the derivative of the charge. So it's going to be the derivative of this one, the derivative of EC 1 minus negative 1 over RCT, okay? So let's just do the derivative of this one. Okay, tell me what's the derivative of this one? This is a constant, okay? So this term will give you 0. So what do you have? We have negative EC, and then chain rule, you get negative 1 over RC over here, and then E negative 1 over RCT, okay? So you see, the C cancels out, you get E over R, and then just this one, negative 1 over RCT, okay? So that's the current. The current is E over R, E negative 1 RCT. Okay, let me start over here. The current is E over R, and then E to the power of negative 1 over RCT. All right? So now let's look at the current at T equals 0. What do you get if you put 0 over here? Tell me. Current at T equals 0 equals what? What is E to the power of 0?
1.
This is 1, right? E to the power of 0, you get 1 at T equals 0. So this is a value at T equals 0. Okay? Now let's look at the limit of I as T approaches infinity. Okay? So that is the limit as T approaches infinity of this one, E over R, E negative 1 over RCT. What's the value of this as T approaches infinity?
0.
0, right? So this is 0. All right. Now we can plot the graph. We have current over here. So at T equals 0, let's say this is E over R. All right. And then it approaches 0 exponentially. So this is the graph of current versus time. Okay. So you see the charge builds up as time goes on, while the current starts at the maximum and then drops to 0. Now I want to tell you a little bit about this one. This factor over here, 1 over RC, it controls how fast it's going to 0. Okay. If this is a very large number, it's going to drop to 0 very, very quickly. Okay. If this is a small number, it drops to 0 very slow. So it's an important quantity. It's called a time constant. Okay. So the expression is very important in electronics when you design circuits. So the expression 1 over RC is called the time constant of the circuit. The time constant of the circuit. Okay, so these are the properties of this kind of circuit. So this is the circuit we've been solving. This is happening now. Oh, so okay, so we have a battery connected to a capacitor, a resistor. So what happens is, you see this starts from a 0 charge. So this battery is going to charge it. But it starts with the maximum current at T equals 0. You have no potential difference over here. The entire potential difference is across this resistor, which is E over R. Okay, so this circuit starts with a current of E over R, and then eventually all the potential difference goes to this one, which is C times I, and the no potential difference at the resistor eventually. Okay, so that's what's happening. All right. Okay. Finally, we're going to look at a charged capacitor connected to a resistor. A charged capacitor, a charged capacitor connected to a resistor. Okay, so in this case, we charge the capacitor fully. Let's say initial charge BQ. That's the initial charge BQ node. Okay. So we start with this capacitor, which is charged. Okay. So you get this charge over in the capacitor, but then you discharge it through a resistor. Okay. That's the problem. This is R over here. Okay. You start with charge Q naught. We want to see how the capacitor discharges through the resistor. We want to see how the rate of discharge depends on C or R. Okay, so we're going to apply Kirchhoff's rule. So if you go, let's start over here. Maybe let's go this way. So it's going to be, well, the current is going to go this way. Maybe let's go this way. Okay, the current is going this way. This is positive charge, I'm going to go this way. All right. So this is in the direction of the current, so it's going to be negative IR. Okay. And then we have minus Q over C. Q over C equals 0. Okay. So this is an equation. And remember, current is derivative of charge with respect to time. Okay. So we have the following. Well, let me take off the negative. It will be dq by dt times R equals negative Q over C. Okay. Now let's divide by R. Let's divide by R. Okay. So we have the following differential equation. dq by dt equals negative 1 over RCQ. Okay. Again, this is a differential equation. The first thing we should do is separation of variables. In this case, we can separate them very easily. Okay. So dq over q equals negative 1 over c dt. All right. Okay. So let's integrate. Let's integrate. The time obviously goes from 0 to t. Okay. Let's say this is t prime over here. All right. And that will give us negative 1 over RCT. How about this one? We're starting with charge Q naught, that's the initial charge. And this will be a function of time. The charge is a function of time. So that's our equation. Okay. So this is ln of the charge going from Q naught to Q of t. Okay. And that equals negative 1 over RCT. All right. So this is ln Q divided by Q naught equals negative 1 over RC times time. All right. So now I change it to exponential, right? When I change to exponential, Q as a function of time divided by Q naught equals E negative 1 over RC times T. You see in this case also the time constant is 1 over RC, okay? And of course, we get the following equation from the other side. So the charge as a function of time is the initial charge Q naught E negative 1 over RC T, okay? So that's how the charge will vary as a function of time, okay? So let's plot it. What is Q at T equals 0? We have already stated it. This would be 1, would be Q naught, right? So we start with Q naught. How about the limit of Q as T approaches infinity? That's going to be going to 0, right? When T goes to infinity, this goes to 0. Okay, so we can plot it now. So the initial charge is Q naught over here, like this. And then at infinity, it goes to 0 like this. Okay, and how fast it goes depends on 1 over RC. Okay, so the time constant in this case is also 1 over RC. All right, how about the current? We just take the derivative. Current is dq by dt. So let's take the derivative. It's going to be Q naught, then you got negative 1 over RC from chain rule, and then E negative 1 over RC times time. Okay. So what is charge divided by capacitance? Let's write this one like this. Q naught over C, and then you've got 1 over R, E negative 1 over RC times T. Can you tell me what this represents? This is initial charge divided by the capacitance. This is the initial potential difference. You see over here? This is initial charge Q naught. The initial potential difference, let's say delta V naught, is Q naught over C. Okay? So this one is delta V naught. Okay? So Q naught over C. Q naught over C equals delta V naught. Okay? That's the initial potential difference. So the current as a function of time is initial potential difference divided by the resistance. So you see, this is the initial current, okay? And then of course you have E negative 1 over RC times T. But we have a negative over here. The negative means it's a derivative, so the derivative is decreasing. That's where the negative comes from. Because the charge decreasing, the derivative is negative, okay? So, I at T equals 0 is, you put 0 over here, you get delta V naught over R, right? Actual negative delta V naught over R. And current at T equals infinity would be 0. Okay? So for this one, let's say this is negative delta V naught over R over here. So, and this goes to 0 like this. Okay? So it goes like this. All right? So these are the properties of this kind of circuit. So let's summarize. So this is, you got a charged capacitor, connect to resistor, okay? So what happens? You start with this potential difference. So the initial current is this potential difference divided by the resistor. So we've got a maximum current of delta V over R. There was the charge, the current keep decreasing, okay? Eventually, there's nothing going on. This becomes zero potential difference. This becomes zero potential difference eventually. That is, the capacitor is discharged fully eventually. Okay. All right. That's it for today. Do you have any questions? No? Do you have any questions?
No.
No?
No,
All right.
Professor,
I'll
thank you.
see you on, well, after spring break, we're going to have a test on the last 4 chapters. Okay?
Oh, Professor, is this chapter will be included in a
No,
test as
no,
well?
no. This chapter is not included.
Okay.
This chapter is going to be in test 3.
Okay.
All right. This chapter will include only chapters 5, 6, 7, 8. This is chapter 9. All right. So I'll be taking our test the Tuesday after spring break. All right. So have a nice spring break.
Yes. Thank you, Professor. I'm
Bye-bye.
sorry for my
Bye.
connectivity issues.
Okay.
Have a great spring break.
You too. Thank you. Bye-bye.